Can you send the file? Oh, yeah. File. There we go. Okay, so today we are going to talk about the stability and instability properties of. Oh, I should change the title, but I forgot. Should be a linear and nonlinear system. Okay, so before we talk about linear system, and I gave you a table about linear system, but now we're talking about when we have nonlinear system, how are we gonna linearize it using Jacobian matrix, and how to determine stability and how to classify your equilibrium solution. So that's our goal for today. Other than that, I also want to talk about a little bit. I mean, not a little bit. It's pretty much all about it. I want to talk about the ecological model, which is the predator and competitors. The model, I'm not sure if you guys talk about it yet, but you will talk about it either this week or next week. So I'm not sure if I'm ahead of schedule again. You did? Okay, cool. So I'm not ahead of your lecture, which is good. It's fairly simple, easy. So I will talk about it a bit when we reach the example because we'll see more in the example. Don't think it's worth for me to type everything up and then do it again. Anyway, okay, nonlinear system. So, let's say we have scalar form x prime equals to f of xy and y prime equals to g of xy, and it's nonlinear, then you can consider the Jacobian matrix, which is this. Okay, so we have f, the partial derivative of f with respect to x and then with respect to y, and then partial derivative of g with respect to x and then with respect to y. And using this matrix, so before we always use x prime equals to ax, we consider the matrix A here, find its what's it called? Eigenvalue and eigenvector. But when you have nonlinear system, you need to find the Jacobian matrix and then consider the eigenvector and eigenvalue of this Jacobian matrix. So whatever you find based on the Jacobian matrix, and then you can use this table. So it's the same table except I added a few more, which is for local linear. Local linear means that it's almost linear. It's like after you linearize it, okay? So it's for nonlinear, but you can linearize it. So you can see that this table, those two parts are almost the same except for where? Except for when we have repeated eigenvalue and when we have center. The rest are identical. So when we have center, so which is when you have pure imaginary, then you could, so instead of just center, you could have spiral points as well. And you don't know if it's stable or unstable. It could be stable, could be unstable. And also when we have repeated ones, you could have spiral points. Before we only have nodal source or nodal sink, but now it's possible that you have a spiral point. So it really depends on your system. But everything else is the same. And then I saw your professor talked about asymptotically stable. They finally did it, but I talked about it a long time ago already. Remember, I showed you the graph, talk about the difference between stable but not asymptotically stable. And so I showed you the graph of those two, stable and asymptotic stable. So I'm not gonna do it again. So we will move on directly to the examples. So again, I'll give you some time to work on the examples as you guys talk about it already. So I guess I'll let you do it yourself. And as always, I'll let you do it yourself and once most of you are finished, I'll take it out. Oh, oops. Seems like it's gone. See, one of you found all the equilibrium point already. 0, 0, yeah. 1, 0, 0, 3 over 4. Half and half. Yep, exactly. Don't look at my solution yet. Try to do it yourself first. Okay, let me take it up and we'll talk about predator and prey model. So for this example, we would first find the equilibrium solution, right? So to find the equilibrium solution, we know that we need to let dx over dt equals to 0 and we need to let dy over dt equals to 0, right? So you want this be 0, you want this to be 0, and you solve those two equations to find our equilibrium solution. So one is when x equals to 0, then y, so if x equals to 0, then this side will be 0 already, right? So you would have either y equals to 0 or y equals to 3 over 4. So x equals to 0, y could be 0, then this side will be 0, or it could be 3 over 4, then this side will be 0 as well. Well, y equals to 0, this side is 0 already, so you look at this part. So y equals to 0, then your x is either 0 or 1. And when both x and y are non-zero, then you need to solve those two equations simultaneously. So this equals to 0, this equals to 0. Solve this equation, you'll get 1 over 2 and 1 over 2. So now we have 4 equilibrium solutions: 0, 0, 0, 3 over 4, 1, 0, 1 over 2, 1 over 2. And now what you need to do is you need to find the Jacobian. So if you let dx over dt equals to f over xy, and dy over dt be gxy, then you can find the Jacobian, which is, well, the partial derivative of f with respect to x, partial derivative of s with respect to y, partial derivative of g with respect to x, and with respect to y. So after you find your Jacobian, you discuss each of your equilibrium solution. So when xy equals to 0, 0, you can plug in 0, 0 in, and you will get this, right? So this is your Jacobian matrix, and then you find your eigenvalue based on this Jacobian matrix. So you get 1 and 3 over 4, and once you found this, you go back to my table and decide what they are. So I used unstable node, but I think your professor would prefer unstable nodal source. It's better because they want you to talk about if it's source or sink. Okay, and then similarly, when you have 1, 0, you plug it back into the Jacobian matrix, you'll get this, and then you have opposite sign, so it's unstable saddle point, and similarly for the other ones. I think this one they want you to talk about sink. So I'm gonna change it to nodal sink. Okay, so this type of question is pretty straightforward, but a lot of computation. Any question about this? Question? Are we good? Good? No? Yeah? No? Good? Cool. So let's talk about the model, because the other 3 examples are exactly like this. So it's pretty boring. Yeah. So the model is, it's called predator and prey model, where your x of t is the number of prey at time t. So the number of prey, so think about the prey, they eat grass, right? So if there is no predator, they'll just get more and more and more. So your natural growth rate is ax, where a is greater than 0. I don't know if this makes sense to you, why it's ax, where a is greater than 0. And yt is the number of predator. So think about predators, they need to eat meat, so they need prey to be there. But if there is no prey, then they're gonna have less and less. So we'll have less and less predators if there's no prey. So alone themselves, it's gonna, their population is gonna decrease. So we have natural growth rate is negative by, where b is greater than 0, so which means they're gonna decrease. Their population is gonna decrease. So this is when they are not together. However, if both are present, so think about this. Now we have prey and we have predators. We put them together. what do you think is gonna happen to our prey and our predator? Is their population is gonna increase or decrease? Just think about it. Instead of thinking about the math, just think about logic. Like logically, which one's gonna decrease, which one's gonna increase, if we put them together. So it's like think about, yes, prey is gonna decrease, right? Because well, predator will eat them. So yes, exactly. So if they are both present, then the population for prey is gonna decline. So when both present, we have interaction rate of decline decline negative pxy in the pre-population. Okay, and we know that well, predator, their population is going to increase. So similarly, we have interaction rate. I'm gonna copy this and make some changes. So there, and now it's gonna be positive. So growth of qxy in the predator population y. Population y. Which means when they are together, you'll get two equations, which is dx over dt equals to ax minus pxy, and then dy over dt equals to negative by plus qxy. So that's when they are together. So this is called the predator-prey system. So let me write it here. So we will have dx over dt equals to ax minus pxy, and then dy over dt equals to minus by plus qxy. So this is the first model we have when you put them together. And the second one is when we have competition system. Where do I write it? Let's write it here. So we will have another system. Oh, this system. This is called predator-prey system. Okay. Predator-prey system. And then we have competition system. So I really don't want you guys to memorize anything. So hopefully this makes sense to you when we talk about the model. Okay, so now we have competition system. So this one is talking about we have two species and they have population xt and y of t, and they compete with each other for food. So it's not about predator and prey anymore. So they will compete for each other for food. So this is let's say two species compete for food. Okay, and because they are competing with each other, you know that when you put both of them together, by the way, if they're competing for food, it's not predator or prey anymore, then both of them would have increasing natural growth rate, right? So both of them, they would have, so without each other, their natural growth rate will be, well, let's say ax. Natural growth rate, it's gonna be positive, so let's say dx dt is a1x and dy dt is a 2x. Now, if you put them together, they're gonna compete for food. So do you think their population is gonna increase or decrease? Decrease, okay? For both, right? Now put together. Okay, we will have, the population will decrease. So now dx dt equals to a1x minus b1x squared. And dy dt equals to a 2x minus b2x squared. So they have really similar ones. But now let's say we add some effect. Okay, so we wait. Why are they both x? Oh, should be y. Sorry, here should be y. Yeah, now it's correct. Yeah. So now let's say we add a negative proton. So we add now. So now let's say now assume computation has effect. So before it's really like a really simple model, now they add another factor to it to make it slightly more complicated. So we assume that the computation has effect of rate of decline, and this rate is proportional to their product, in which population in each population that is proportional to xy. So now they have interaction. So xy, which means now my new one is gonna be, so my new equation is gonna be, so I'm just gonna copy this and add another factor. So now this is my new one. I'm gonna minus c1xy and minus c2xy. Okay, so this new system, this one is the one that's being tested the most. Okay, so this one is called computation system. Most likely they will test you on this because it's the most complicated one, at least in 244. Okay, so this one is the most important one, and very likely what will ask you is it will ask you if those two species they can coexist. So our question is, can those two species coexist? So if they cannot coexist, it means one of the species is gonna go extinct, right? So that's what it means. So how do we know? We compute C1, C2, and B1, B2. So C1, C2, and B1, B2. So if C1, C2 is less than B1, B2, okay, then they will coexist. They can coexist. 2, if C1, C2 is greater than B1, B2, then one of them, then one will become extinct. Okay, so if one of them will become extinct, when you take the limit of t goes to infinity, then one of them must be 0, right? Because, well, the population goes to 0. So one of them must be 0. So one of those two will be 0. One of those is 0. Okay? That's it. That's everything about this predator and prey thing. So basically, most likely what they will ask is they will ask you to find and classify all the equilibrium solutions, and then they'll ask, well, if is this system, for this system, can those two species coexist? And if they can, compute the limit. If they cannot, compute the limit. For the previous question, yeah? Do they coexist? Well, you tell me. What's my C1, C2, and B1, B2? Basically, you just need to compute this. Okay, so let's write it down. What is my B1? Anyone? B1 is what? 1. C1 is it's 1, not minus 1, because it's minus here. Minus B1, minus C1. So it's 1. Okay, C1 is 1 as well. Okay, what about B2? B2 is 1. And C2 is 1 over 2. Right? So now B1, B2 equals to 1, which is greater than C1, C2. That's 1 over 2. So can they coexist? So B1, B2 is greater than C1, C2, which means they can. So they can coexist. How I found the numbers? Yeah, sure. So this is what you need to compare with. So copy, let me put it here so you can compare. So this is what we have, okay? If you write this as x minus x squared minus xy, you can write this as 3y over 4 minus y squared minus 1 over 2xy, correct? So now you compare those two, okay? So compare this to this. You'll see that, well, A1 equals to 1, B1 is 1, and C1 is 1 as well, right? And then compare this with this. You'll see that, well, A1 is 3 over 4, A2 is 3 over 4, B2 is 1, and C2 is 1 over 2. So once you find your B1, B2, C1, C2, you can compute this and decide if they can coexist or not. Any other question? Okay, cool. So my question is, look at example 2 and tell me, can they coexist or not? There are 4 equilibrium points. Yep. I will give you a solution for the equilibrium solution. So you can try it and compare yours with my solution. I think I wrote a complete solution, which is here. So I'll copy paste it. This is my complete solution. Oops, too big. There we go. And I want to change this to unstable nodal source because it seems like they actually care about this. Stable, both are negative, so this is symptotically stable nodal sink. And here, similarly, and here, stable setup point. Yeah. Anyway, did anyone finish finding B1, B2, and C1, C2? Okay, so someone said the B1 is 1, yeah, B2, C1 is 1, B2 is -25, so they cannot coexist, exactly. And someone asked, what if C1, C2 equals to B1, B2? It's very unlikely to happen because that means your the model for both species are the same, which is very unlikely to happen because, well, if you have two different species, the factor that, like the the factor that affects their population is very unlikely they will be the same. So it's we don't talk about when they are equal because they will be not equal. This model is really simple already, so I don't think they'll ever be equal. But anyway, yeah, they cannot coexist. Yeah, exactly. So there's not much I need to talk about, to be honest. But we will talk about this a bit. Let's see this. So here we have to find the equilibrium solution. So as before, you let this equals to 0, you let this equals to 0, and then you can find the equilibrium solution, which is 0, 0, 0, 2, and 1, 0. And when x and y are both non-zero, you solve those two equations simultaneously, you will get 0.5 and 0.5, just as before. And then you compute the Jacobian matrix, and then plug those back in, find the eigenvalue, and compare it to the table, decide if they're stable or unstable, or which type of equilibrium solution they are. So there's not much I want to say. How do we find the limit? You need to compute xt or yt approach to 0. So basically you need to kind of solve it first. So it's the limit of t goes to infinity of xt, and then the limit of t goes to infinity of yt. So after you compute that, you can see which of the species will go extinct. However, I think most likely they will ask you to use graphing calculator to see the limit. So I don't think they want you to solve the equation. So let me see your homework just to make sure what I said is correct. Let me check. So homework 1 is matrix exponential and then non-homogeneous equation. We covered already, very short. Yeah, we covered 1 already. 2 is this. Yeah. To find critical points, compute Jacobian, sketch the phase portrait. Yeah, we know all those already. Make a conclusion, can green, selfish, and can they coexist? Which we covered already as well. Oh, there we go. Here, if yes, use a picture to find limit sizes of populations, limits of xt and yt as t goes to infinity. So they want you to use a graphing calculator to find the limit instead of solving the whole thing. But if you wanna compute this yourself, then you need to solve x and y. If you don't want to use the graphing calculator, which I think you should use it, because just solving it is kind of pain. Anyway, any other question? Question? Anything else? Okay, seems like no one has any question. We have 5 more minutes. I don't think we'll have time to do everything, so I will ask you if they can coexist in this and example 4. So 3 and 4 decide if they can coexist. And the rest of the solution I'll post it on Quarkus, so you don't have to worry. Okay, since 9 is greater than 8, okay, exactly. So 3, they cannot coexist. What about 4? Can they? Okay, so 4, they can coexist. Yes, exactly. Okay, so I will post the find and classify all equilibrium solution, the other things, on Quarkus tonight, or I don't know, after my tutorials. I'll write the solution down and then I'll post it on Quarkus. But yeah, I think that's it for this tutorial. Next week, I believe that's going to be our final tutorial, last tutorial. Is it? I think so. And oh, and don't forget, this Friday is Good Friday, so no class, no tutorial, nothing. You have a long weekend. Have a good week, everyone. Is the last tutorial going to be about final review? I don't think so because they haven't covered everything in class yet. We still have 8.1, 8.2, and 2.4. So right now I covered 6.1 to 6.3, but next week we have more material, so I don't think it's final review. Okay. See you guys.